In this video, we are going to calculate the reaction forces of a beam with uniformly distributed loads and a point load. This is an exam question from January 2021. On this beam, we have a point load that is acting at a single point, and we also have a uniformly distributed load of 5.5 kilonewtons per meter that is acting over the entire length of the beam. In this type of problems, we are going to consider that the beam is a simply supported beam, which means that the reaction forces are only vertical. There are no horizontal reaction forces. R1 is the reaction force at the left support, and R2 is the reaction force at the right support. The day of the exam, you will have a booklet with the formulas that you may need. The ones that we are going to use in this problem are the equations of equilibrium and the formula of a moment of a force. These are the equations of equilibrium. The first one says that the sum of forces in the horizontal direction is 0. As I said before, we will consider a simply supported beam. This type of beam doesn't have any horizontal reaction forces, only vertical ones. So this means that we won't be using this equation of equilibrium. We are going to use these two. This one means that the sum of the forces in the vertical direction is 0. Here we have the vertical forces. We need to add them together and equal 0. This equation of equilibrium means that the sum of the moments around the point is 0. We need to select the point, calculate the moments caused by these forces, add them together and equal 0. We will also be using the formula of a moment of a force, which is force times distance. This is the exam question with the scenario that explains that the beam is part of a bridge deck. What we have to calculate is the reaction force RB, which is the reaction force on the right. To solve this type of problems, we are going to follow these steps. First one, the sum of the forces in the vertical direction is 0. Second one, the sum of the moments around the point is 0. We will have to select the pivot to calculate the moments, and we need to know if the moments that we are calculating are clockwise or anti-clockwise. And in the third step, we need to solve the two simultaneous equations that we are getting from steps 1 and 2. Whenever we have a uniformly distributed load, we need to convert it into a point load. This uniformly distributed load is 5.5 kilonewtons per meter. This means that on every meter of the beam, there is a load of 5.5 kilonewtons. To convert it into a point load, we need to multiply 5.5 kilonewtons times 22 meters, which is 121 kilonewtons per meter, applied in the middle of the uniformly distributed load, which in this case it's the middle of the beam. Step 1. The sum of the forces in the vertical direction is 0. We have 4 forces, and we need to find out which ones are positive and which ones are negative. The ones going down are going to be negative. The two reaction forces go up, which means that are positive. The sum of the vertical forces is 0. The positive ones are the reaction forces R1 and R2, and the forces of 12 kilonewtons and 121 kilonewtons are negative because they go down. So minus 12 minus 121 equal 0. R1 plus R2 minus 133 equal 0. I'm going to rearrange this equation so the number is on the other side of the equation. To do this, I need to add 133 on both parts of the equation. R1 plus R2 minus 133 plus 133 is 0 equal 133. And we will keep this equation for later. Step 2. The sum of the moments around a point is 0. This point is called the pivot, and we need to place it on the beam. I'm going to select the pivot on the left end of the beam. Now we need to determine if the moments caused by the forces are clockwise or anti-clockwise. I am going to start with the force of 12 kilonewtons, but the force of 121 kilonewtons is going to be the same. So the force is going to push down the beam, and the beam is going to turn in a clockwise direction. This means that the moment is positive. Now I'm going to continue with the reaction force R2. This force is going to push up the beam, and the beam is going to turn in an anti-clockwise direction. So the moment is going to be negative. Now I will start calculating the moments of each of the forces. The formula of the moment of the force is force times distance. The distance is between the force and the pivot. The moment of the force of 12 kilonewtons equals the force, which is 12, times the distance from the force to the pivot, which is 6 meters. 12 times 6 is 72 kilonewtons meter. The moment of the force of 121 equals the force 121 times the distance between the force and the pivot, which is 11 meters. 121 times 11 is 1331 kilonewtons meter. And the moment of the reaction force 2 equal the force, which is the reaction force R2, we still don't know its value, times the distance between the force and the pivot, which is 22. This is 22 R2 kilonewtons meter. The moments of these two forces are clockwise, which means that they are positive. And the moment of the reaction force 2 is anti-clockwise, which means that it's negative. Now I can apply the equation of equilibrium that says that the sum of the moments around the pivot is 0. 72 plus 1331 minus 22 R2 equal 0. 72 plus 1331 is 1403 minus 22 R2. I need to rearrange this equation, so I'm going to plus 22 R2 on both parts of the equation. 1403 equals 22 R2. I need to rearrange it again to get rid of this 22. To do this, I can divide by 22 on both parts of the equation. So 1403 divided by 22 equals R2. R2 equals 63.77. I have rounded it to 2 decimal places, kilonewtons. And this is the answer. In this problem, they were only asking for the reaction force at the right end. This means that in this problem, we didn't have to use step 1. But in most of the problems, they are going to ask for both reactions at the left and right ends. So I think it's important to get used to follow the same steps every time. If we want to answer this problem, we have finished, because the reaction force at the right end is 63.77. But just to have a little more of practice, I am going to calculate the reaction force at the left end as well. These are the two results that we got on steps 1 and 2 that we are going to need now to calculate R1. In step 1, we got this equation. R1 plus R2 equal 133. R2 is 63.77. R1 plus 63.77 equal 133. I need to rearrange this equation. I'm going to minus 63.77 on both parts of the equation. R1 equal 133 minus 63.77, and this is 69.33 kilonewtons, and this is the reaction force at the left end.